So again, something I wanna give you kind of good news. I know so far things like very dry, like it's kind of hard to understand, but please be patient, and I promise you things will be completely different once we do our first numerical example. One more thing is, as a good news is, uh, you can see we're turning our slab, our one-way slab, into a 1 meter wide beam. We're turning our one-way slab into a 1 meter wide beam. And because we already sweat and we spent time on beam design, you will see lots of similarities. I would say 90%. The design of one-way slab is 90% identical to my beam design. A lot of similarity with few or minor changes. So what happens here before I show you the numerical example? There are some specific requirements for the slab design. There are some specific design requirement from the code. And what we will do is, after we do that, we will simply have to give you some numerical example, okay? I think my slides are not in the right order, so we'll see, but this is later on. But anyway, for now, I simply snap all the requirement or all the extra requirement for the slab from the code. It's in one slide. So on the slides right now, those are all slab specific code requirement. Okay. You can see there are not so many, and we will do all of them. So here we go. Here is my first requirement. So the code requires a minimum reinforcement in your slab, same as the beam. So the beam, if you guys remember, the code requires minimum reinforcement. The difference is we use different formula. So in the slab, if you guys remember, in the beam, I'll show you if I remember correctly. This was the I cannot remember even. Oh my God, I'm getting old. So 0.06 multiplied by square root of f prime c divided by f field multiplied by b times h. Not 100% sure, but it's around the same. So the area of steel minimum for your beam, it looks like it's 0.06 multiplied by square root f prime c divided by f field multiplied by the dimensions of your beam. So in the slab, we don't use the same equation. Instead, we use a different equation. And the different equation is, it is 0.002 multiplied by the cross section area of your slab strip. So a minimum area of reinforcement of 2/1000 multiplied by area gross, which is what area gross of what? Of your design strip. And remember, and we'll talk about this one later on, this has to be provided in both directions. Look at this name, in each direction. I'll talk about this one shortly, not now, but shortly, maybe in 5 minutes. Okay, now, what else? What are other requirements? Look at this, please. So the other requirement is here. So the other requirement is about the spacing between the rebar. The spacing between the rebar. So guys, probably I need to show you a Revit model, and so to understand what is the spacing. So look up my screen. Look up my screen, and so this is a slab reinforcement. I make it in Revit, and if you go to the section, if I go to the section, so this is a section through the slab, and please look up my screen. So look at the screen. So there's a rebar here, and there is a rebar over there. So what is the spacing? Simply between the center line of this rebar to the center line of this rebar. This is called spacing. So the code has some requirement for the spacing. It doesn't allow the spacing to be so big. It controls the spacing between the bars. How much? Let's read. So you can read in walls and one-way slab. So this clause here applies for walls and applies for slabs. And the principal reinforcement, the principal, look at this name, very important, huh? The principal reinforcement, I will mention this name in 5 minutes again. Principal reinforcement. Principal reinforcement shall be not spaced further apart than the smaller of. So looks like we have to make comparison. We have to estimate two numbers and pick the minimum. So the smaller of 3. So here is your first number, huh? So 3 times the wall or the slab thickness. That's your first number, or 500 millimeters. Okay, guys, all I'm asking for now, I know it's kind of hard to follow the way they write it, but please be patient at this point of time. Really, what I want you to understand is there is a maximum spacing between the rebar in your slab. How much? We have to find two numbers, and those numbers is 3 times the thickness of your slab or 500 mil. So in any slab, looks like, we cannot space our rebar like further than 500 mil. So if you see a slab that has 2 feet in between the rebar, this is a mistake because it doesn't meet code requirement. Okay, now we know that there is a minimum area of steel and there is a maximum spacing between the rebar. And I'm going to show you by numbers. So please don't be worried for now on how this play in the slab design, because there is a complete design example in my slide that tells you how do we check those and how we ensure that those are happening when we do the design. Okay, now another condition here, which I know it will look confusing for now, but just give me 5 minutes and I will promise you I will cover those. Minimum reinforcement shall not be spaced further than the smaller of 5 times the slab thickness or 500 mil. So looks like there is two clause here in the code. One is referring to, look at this please, to the principal reinforcement, and the other one is talking about minimum reinforcement. I think my next slide will explain more about those. Let's see. So my next slide is saying, you know what? Here is a more details about one-way slab. Guys, same example. If I have 4 meter and 8 meter, what do you think? 4 and 8, and my beams are all around. So what do you think? Is that one way or two ways?
Two-way?
That
Two way, 8 and 4, and my beams are all around. So
One
it's
way.
one. It's one way.
Oh,
It's
it's
one
one way.
way.
yes,
It says right
I
there.
remember when I talked to Mike and I said 2 is included. So 2 and above. So anything below 2 is two-way.
Yeah.
Anything above 2 or above, it means it's so elongated and it will work as one way because one direction is so short and so strong and it will take 100% of the load. Okay? Okay, now so we say our slab is one way. What does it mean? It means the load will go 100%. Look at the name, 100% will go where? Into the stronger direction, which is the shorter, huh? So you can see, look at my screen, look at my screen. So here I have 100%, load will go this way. And where is my design strip? What do you think? My design strip should go this way, should go this way, or should go the other way? What do you think?
Should go into the
Short way.
shortest one.
Exactly. So my design strip will have to cover the load because 100% of the load go this way. Let me ask you, the design strip here is continuous or simply supported?
Simply supported.
Simply supported. And we can find the moment. We can say W L squared over 8 because simply supported. And we can find the moment. And once we know the moment, we can find area of steel.
Mhm.
Okay, we can find area of steel. What do we call the reinforcement in this direction? We call it main or principal. We call this one main or principal. Now I know some of you will say, okay, fine, so we found, let's say I need 5 bars per meter, like a 10 m every 200 mil. Okay, and what I will do is, because all those design strip, what do you think? What should I do? So I'm gonna put in this meter 5 bars. I'm asking you, what should I do with the next one?
Leave it.
No, so leave it. It means I'm gonna put here 5 bars in this 1 meter and no reinforcement in the left and the right, right? Is that what you're saying?
For sure, there is a reinforcement on the left and right.
Guys, listen, that's very simple. Every one of those design strip from grid line G to grid line H, they are
You
identical. They are twins because
you
they share the
times
same
it by
span.
8. Yeah.
So
Excuse me.
suppose like
Excuse me.
the solo all have 5 rebars.
Exactly. All of them are identical. Why identical? Look at this. They share the same span, which is 4 meter. They carry the same load. Everything they have the same kind of support, like 2 support point. So everything the same. So they are identical, which means if this design strip needs 5 bars, looks like every meter will get 5 bars. Are you guys following?
Yeah, that's what I mean. Like, once what you did
Is
in
that what you
that,
said?
because
Is that what you said? Forget about what you mean. I don't get it. Like, is that what you said?
yeah, I just maybe don't know how to express it. But
Oh my
once
God.
what you did in that thing there, you do this. That means you don't do anything any more calculation. That means you follow what you have done in that first trip because they're all identical.
Okay, thank you. Okay, guys, so listen. So all we have to do is we take one design strip, we find the moment, we find area of steel, and we simply have to apply area of steel in all those design strip. Okay? So which means we apply the same reinforcement between grid line H and grid line G. But let me ask you, do we add any reinforcement perpendicular to this? This a plan view, huh? A plan view. So like looks like my main reinforcement that I got from the moment, I'm gonna place them all of them parallel to my design strip. They will span between grid line 9 and H. I'm asking you, and we call them principal or main reinforcement. Now, do I need to add reinforcement perpendicular to my main reinforcement? Like going between grid line G and grid line H as my blue line, yes, you will have to do that. And here is the answer why. So I'm in writing, everything is written here on the left. I said shorter direction is called the main direction or principal. Probably I have to change my writing to match the code because the code is referring here to principal. So probably my writing has to match. So the reinforcement, the principal reinforcement of the principal direction will simply carry the bending moment because 100% of the load going into this and 0% of the load going here. 100 and 0. And that's why it's called one way. Now, the other direction carries 0% of the load. It's called transverse direction. We need to provide a minimum reinforcement in the transverse direction. Why? Because the code said that. Look at this. So the code says a minimum area of reinforcement of 0.002 AG shall be provided in each direction. Okay? So because we have zero load going into the transverse direction, zero load. So there is zero moment and there is zero area of steel, but the code says put the minimum. So we will have to add here in the transverse section, we add the minimum. Why? Because two those reasons. Number one, there are some stresses that we never accounted for, like thermal stresses and shrinkage stresses. And then finally, for the slab integrity, because yes, in our analysis, we think about our slab as simply so many adjacent strip beams, but at the end of the day, it is not a beam. It is a slab, and a slab is a plate element, and it is a two-dimensional element, and that's why we have to add reinforcement in the transverse direction for the slab integrity, because at the end of the day, the slab is two-dimensional element like a plate, and even we deal with it in our design simplified as a smaller like a 1 meter wide design strip, but those are not separated. Those are simply connected to each other, and that's why we have to add transverse reinforcement. Does it make sense for you guys? Why do we add transverse reinforcement?
Yes.
Okay, so please, for a one-way slab, 100% of the load will go into one direction, which is the shorter, and we know how to find the moment because we add all the loads. We look at the slab, is it simply supported? We find the moment, and from the moment we find area of steel, and we say, for example, let's add 10 m bar at 200 mil on center in this design strip. Okay, and wherever the design strip is still applicable, it means identical, I can apply the same design. That's the main direction. How about the transverse direction? We add minimum, not based on bending moment, it is based on zero bending moment. So then why we add them? For slab integrity, because the slab is a two-dimensional element, even if we simplify it into adjacent design strip, but at the end of the day it will work and behave as a plate element. And number two, there are some extra stresses that we never accounted for, like shrinkage and thermal stresses, and that's why we add the minimum. This is the big picture, guys. Now time to put everything you learned so far in a numerical example. Are you guys ready?
Yeah.
I'll give you a few minutes because I think I'm going very fast. I'll give you a few minutes to kind of catch up, and if you want to add some notes to your class notes, do that please now if you want. Okay, guys, let's get back and do our first numerical example. So my first numerical example here, and it is very detailed. I take you to the end by numbers, so I'm not missing anything, I'm assuming. And so we always start from a plan view. So on the right side here, there's a plan view, and there's some other information on the left. And I'm going to spend some time with you guys to need to understand what's going on. And I always say that don't jump right away and answer. Don't do that. Please spend some time, try to read well the plan view. Okay. So the plan view here is we have an area that is 5 meter by 16 meter. So that's the total area, 5 by 16. Please identify the grid lines. So grid lines, we have grid line 1 and 2, and vertical grid lines is grid line A, B, and C. So we have a floor plan, and this floor plan is supported on two beam lines. One beam line is on grid line number 2. Another beam line is grid line number 1. So I'm going to show you guys where are those. So this is a beam line here, and this is a beam line over there. And I'm going to say it one more time, guys, and I said this in the other in beam design. How many beams do we have? Do we have 4 beams or 2 beams? That's probably
Two.
for Michael, huh?
Two.
This question is
Beams,
probably for
two
Michael as well.
beams.
Michael, do we have 4 simply supported beam or we have 2 continuous beams? Michael, are you there?
Sorry, what?
So there is a question for you that goes along the same question that you asked in the break. In this plan view, do we have 4 simply supported beams or we have 2 continuous beams?
4 simply supported.
So it means I haven't answered your question, by the way, because you are not following. So look at this, please. I'm going to say it one more time. So Michael is saying we have a beam that goes from here to there, and then another beam that goes from here to there, and then a third one that goes from here to there, and then a fourth one that goes from here to there, and all of them, they are simply supported. Is that what you're saying? Or need to change your answer?
No. Sorry, I was focused on the slab. The beams are continuous.
The
Are they not?
beams are continuous. So yes, the answer is very important, guys. So we do have here, we have 2 continuous beams. 2 continuous beams. Yes, for the slab, when you look at the slab, again, how we deal with it, please, wait, I'm going to show you the standard way that you have to think about the slab. I'm going to give you the standard way on how we approach the slab. Okay. Now, let me give you the rest. So we have 6 columns. So we have 6 columns and all the column dimensions are mentioned over there. So this column here is 250 by 800. The beam is 250 by 650. We have total of 6 columns. So I give you here some information will help us with the design. Rebar is 400. My concrete compressive strength is 25 MPa. Concrete cover for the slab. Remember, this is a slab design, so this is doesn't work for beams. Beams minimum is 30 millimeter, but for slabs, cover sometimes is 20 mils. Okay, so that's concrete cover for the slab. We have SDL, which is superimposed dead load on the slab, 1.5 kPa, and that includes partition, mechanical, electrical, anything that hangs from the slab, it should be included here. And 4.8 is the live load requirement. When we design this slab at the end, I need to use 15M for slab reinforcement, and the slab is interior slab. Okay. Now, please read on the left here. As I said before, don't waste your time to think about the slab dimensions without looking at the support of the slab. So let me ask you, do we have beams on this side? Yes or no?
No.
No.
Do we have beams on this side?
No.
So please, don't waste your time in the exam or in the assignment to estimate R. That's not required, because whatever the R, it doesn't matter, because the slab has only one way to bend, because there's only one, like 2 sides of the slab that are being supported. That's why, please don't waste your time. Don't estimate the R, which is written over there. So the slab is one way, not because of the shape of the slab, not because R exceeded 2, which is the case. If you divide 16 divided by 8, what happens is you will get more than 2. But that's not the way. One-way slab is not because the R is more than 2. It's because there's no beam on this side and on this side. Okay? Please do the following. Number 1, check if the slab is supported on 4 edges. If the slab is supported on 4 edges, then please estimate the R. If the R is more than 2 or equal, then it's one-way slab. If it is less, then it's two-way slab. Okay? Now, okay, ask.
So can we assume if it's not supported on all 4 sides, do we assume it's a one-way slab?
It's not assumption. If the slab is supported only on 2 opposite directions, not on 4 sides, then the slab will have only one way to bend. If you have time, probably I'm gonna stop, guys. I'm gonna stop my sharing, and please look at my screen. Look at my camera. So look at this, guys. Look at this. So if I look at my hand is the support. So I am providing a beam on this side and this side. Look at how the slab bends or how the paper bends. It bends in one direction. In one direction. So that's not an assumption, that's a behavior. If you provide beams on two opposite directions, but not on four sides, the slab will be one way regardless the dimension of your slab. I said this probably 10 times by now. Is everybody clear? Hello?
Yep.
Yes.
Okay, now, so guys, I'll go back to my example again. Again, the way you think about it. Number one, ask yourself, do I have beams all around? If the answer is yes, then find the R. If the answer is no, don't waste your time and right away say my slab will simply act as one way. And this, when we say one way, it has no business with the shorter or the longer. No business. There's only support. Even guys, I mean, I know it's not going to happen, but if I scratch this number and I make this number, like let's say 17 meter, if this number is 17, you know what happens? It's going to span on the 17th meter because simply there is a beam here and beam here. So once the beams are on two opposite sides, not all the four sides, the slab will act in one way. Not the shorter, not the longer. It is where you have beams. Hopefully this is clear 100 times. Now, one good question, guys. How many slab panels do we have? Can anybody answer this question? How many slab panels do we have? Do we have one or two or three or four?
Two.
We have only one slab panel. You can see there is no beams to cut your slab or chop your slab into several sections. The whole slab is one piece. The whole slab from grid line C to grid line A, it is one piece. You cannot find any beams in between. And that's why your slab is one big panel. 16 by 5 meters. Now, next is, now we know after all this discussion that my slab is one way. And look at the blue dimension line. It means 100% of the load will go into this direction. Now, how many design strips should I do?
Only one.
One. Okay. Here is it's on the slide. So I said only one design strip is required. But I'm gonna share with you guys what will be the answer because this is kind of a common question on the exam, on the midterm exam number 2. I give you a plan view and I said, okay, tell me how many design strips do you need? You can see sometimes we need like in this example here, we needed 5, total of 5 design strips. Okay, but you can see all of them, they are different. Look at the design strips, all of them, they are different. Okay, so I'll tell you the answer here. When I give this question in the exam, some of you will say, hey, Tahir, I need 16 design strip. What do you think? Do I need 16 design strips?
No, you don't need it.
But I'll tell you, some in the exam will do that. Will tell me I need 16. They think this one and the next one and next one, those are different. It is the same design strip because all of them, they have the same span. All of them, they have the same support configuration and they are identical. So to solve this problem, honestly, I need only one design strip. And when I'm able to design it, then because all of them are identical, I can apply the same design on those 16 meters. Now, let's go to the next slide. So the next slide is, you can see here, I never mentioned my my slab thickness. Okay, let me ask you, do we need slab thickness? Do we need slab thickness? Let's see.
Okay.
Do we need slab thickness? I mean, is it required for the design? Do I need to know what is the slab thickness in my design?
If you are looking for the load, the load, yes, you need the slab thickness.
So Jill is saying, yes, of course. I need to, when I find the load, the slab has to support itself. So this is part of the self weight. I need to find what is the slab thickness. Makes sense, correct. But is it only for to find the load, or I need slab thickness for something else in my design? Guys, remember beams, huh? Please don't focus so much for slab. At the end of the day, your slab, we're turning it into a design strip beam, like 1 meter wide beam. Do I need the slab thickness for my design in addition to finding the self weight of the slab?
Yes.
Okay, Martin, can you tell me explicitly why?
For the rebar spacing.
Oh, okay. You went, I think you looked at the slides and you said it, the spacing between the rebar should not exceed the 3H or 3 slab thickness, right? But I'm asking you, in your design, can you find area of steel without knowing the thickness of your slab or beam?
Oh yeah, that's the way how you find it. That's why you need the slab thickness.
Okay, guys, look at this, please. You guys remember when we have something called the H and something called the D? Can anybody remind me what's H, what's D?
Okay, yeah. H is the total height of the beam, and the D is the effective depth of the beam.
Okay, are they connected?
They are connected.
Exactly, guys. So look at this, please. So look at my slides one more time. So you cannot proceed in your, if the H is not given, and I have to be clear, if I give you slab thickness, then you must use it. And please ignore slab thickness if I give it to you. So do the following only and only if the thickness is not given to you. Are you following? So this table is new or old? Have you seen this table before?
Yes.
Where did you see this table before?
When we design our beam.
Beams. So guys, you can see on my slide, this table, we use it to find the thickness of the beam or the one-way slab, okay? And what we did is we simply look at the table, and you can see here, before I used this row here, one-way beams or ribbed one-way slab, but this row here, this row over there, this one here, it is solid one-way slab. And it depends on the structural system of your slab. If it's cantilever, you take this number. If it is simply supported, use this number. And I will talk about this one sometime next class. What does it mean one end continuous, and what does it mean two end continuous? But for now, I'm asking you, how do we call the design strip? I think Michael can say that very comfortably, huh? The design strip is it continuous?
Simply supported.
Simply supported. Wow, great. So yeah, it is simply supported because it is one span. It has only two support points, one here on the beam, another point here on the beam, and it's simply supported. And that's why here is my column, and that's how I find the thickness of my slab, Ln over 20. So now, how much is my Ln? Yeah, I'll have to show you here. So what I did is I cut section through my design strip. And which is here. You can see I have a section here, and I create this section using my Revit. So here is my section here. An actual section, by the way, actual section. So from grid line 1 to 2, there is a 5 meter. My beams are 250 wide. So this beam is 250 wide, and this beam as well. And that's why the clear span from this point here, where the slab strip leaves the beam, to where it finds the beam one more time, this clear span is 4.75 meter. How did I get the beam width? It's over there. Please, in the exam or in the assignment, don't ask me. The beam width is here, 250 by 650. So if the beam width is 250, I'll dimension that for you. So if the beam width is 250, so this is 250, it's like 0.25. Then you guys know you can find your clear span. So all you have to do is, you can see my clear span is 4750, and then I can go here and I divide 4750 by 20. Why 20? It's from there. Look at this, please. It is from there, from the table. So 4750 divided by 20, it means the minimum thickness of this one-way slab, it is 238 millimeters. And here is the rule of rounding. Remember, we never build slabs to this number. What do you think, Gord? Can we build slab to 138 mils? What do you think?
No.
So can you tell me, like, what is the rule? Like, what did you see on what did you build? Like, did you build like a 135 mil slab?
No, I don't think you can build that one either.
Yeah, so really the slab, the rounding rule is we round the thickness of the slab to the nearest 10 mils. 10 mils. In beams, it's different. We round it to the nearest 50 mils, 2 inches. So we build the beams 14 inches or 16 inches or 18 inches in metric, 400, 450, 500, 550, and so on and so forth. For slabs, we go by and to the nearest 10 mils. And I'll tell you something also, you will be surprised. We typically round it to nearest half inch. Half inch. When you look at the drawing, you'll see drawing says 6-inch slab, 6.5 inch slab, 7-inch slab, 8-inch slab. Although we are in Canada and we're not using those imperial units, but still we use the inch. So anyway, so what I did here, I simply chose, it's supposed to be 240, but I chose 250. Okay, I chose thickness of the slab 250. I need to remind you, if I'm designing a high-rise building that has 100 of those floors, have 100 of those floors, should I go easy when I pick from 238 to 250?
Yes.
You guys not really studying, you're not following the discussion. I said this last class, and I said we have to really cut the slab thickness to the minimum we can. So don't just ignore, you say, okay, jump straight from 238 to 250. It means 12 millimeter extra. And if you multiply the 12 millimeter extra, multiply by the area of the floor, by how many floors, multiply by 24, you are penalizing your concrete foundation and your seismic design. I said this last class, how many times? I cannot remember, so many times.
So how was I wrong?
Huh?
How was I wrong?
Because you're adding too much weight.
Because I ask if I'm designing a high-rise building that have so many of these floors, should I go straight easy as I say, you know what, to 38, go straight to 250, or I should go to the 240?
Oh, I guess I misheard what you meant. I thought you were asking, do we go higher when we're building like high rises? I meant like, no, we're not supposed to, because then you're just adding a lot of weight.
Okay, sorry, sir, no problem. Okay, so again, here in this class, I'm not really building a high-rise building. Let's say 1 floor, so it doesn't really matter if I go from 240 to 250. I chose here 250. Okay, so it means 10-inch slab. So 250 is a 10-inch slab. Now, what happened next is I'm going to estimate the load. So the load here is how much? This is, by the way, here is the tricky part, and this is confusing. And please pay attention. So if you're sleeping for so long, please wake up now, because this is different from how did we do it for the beam. And I think Jelly brought up a question and said, what is the trip width of my design strip? Did we answer this question already? What is the trip width of my design strip?
Oh,
What is my trip width of design strip?
1 meter.
1 meter. And you know what? If you don't see the 1 meter, probably I'll show it here. What if I do some line work? If I go do this, and I do this, I'm trying to turn things into 3D, and I do this. Okay, so this is my 1 meter design strip. So where is the 1 meter? It's very simple. It's from here. I'm sorry. It is from here, from this point here to this point here. That is the width of my design strip. So this is your 1 meter. Okay, so that's your 1 meter design strip. Of course, because this is a section, a section through, you don't see the width of your design strip. And that's why, look at here, when we find dead load, we just have to multiply the thickness of your slab times gamma concrete. So where is the trip width? It's 1. The 1 is here, because if we multiply anything by 1, it doesn't show, huh? It doesn't affect my numbers. And then finally, I multiply my SDL, and SDL multiply by 1, because the trip width is 1. This is different from beams. From beams, what we do is we multiply, or sorry, add the thickness of the slab, multiply by 24 plus SDL, and I take this whole term, multiply it by the trip width. What I don't multiply by the trip width is the self weight of the beam. Okay, here the trip width is equal to 1. Please take a note. For a slab, we just have to multiply thickness of the slab by the gamma concrete plus SDL. Why is that? Because think about the 1. It is 1 meter wide design strip. Again, live load in beams, I multiply live load by, can I get it? Can I get some help? In beams, I multiply live load by
the tributary loads, a tributary area.
width.
A tributary width, not area.
Okay. Why here same 4.8? Because strip width is 1. That's why I get the live load. And then how do we get W factored, like W sub F? It means I have to do load combination number 1, where I multiply my dead load times 1.4, and then load case number 2, I multiply my dead load multiplied by 1.25 plus my live load multiplied by 1.5. Looks like load case number 2 will govern. Now, how can I find the moment? Very simple. Guys, always don't forget, please turn and show me what is the free body diagram. So this section, this is an actual section, huh? This one is actual section through my design strip. But what's the free body diagram? Which shows only center line. So here is center line. Here is one support, which is the beam. Here is one support, which is the beam. And looks like, as Michael said, my design strip is simply supported. If my design is simply supported and my span is 4.75, what is the moment? What is the moment?
4.75 times 16.6.
16.6.
That's your WF. Your WF is 16.6.
Multiplied by what? That's W.
By the width, by your width.
Squared.
14 points. Yeah, WL squared over 8. WL squared over 8. That should be your
Guys,
moment.
don't forget, for simply supported beam only, not cantilever, not continuous beam, we use a very simple formula, which is WL squared over 8. Remember, the L here is LN, so the clear span, and then 4.75 squared over 8. So that's my moment. So remember, what's the shape of the bending moment? The shape will look like a parabola, so which means it goes like this. And then I go here. Sorry. It's not easy to draw in PDF. Huh? So this is the shape of your parabola, and the maximum value is over there with a value of WL squared over 8. So this number is how much? This one is 46.82 kilo Newton meter. Okay? Okay, guys. I think I'm going to stop in here, because next is simply, we know the moment, and next class, you will see there is no invention. I'm going to use the formula or the table to find my area of steel. Any questions so far?
Yeah, Tahir, can you explain the 1 meter again, how we got the tributary width?
I'm not going to say it again. You just have to look at my drawing here when I kept saying we will simply convert our complicated slab system into 1 meter wide design strips. And if you want to get Mahdi method and use 2 meter wide design strip, that's okay. But remember, when you have your design strip 2 meter wide, look at this. It means all your numbers here will be multiplied by 2, which means this number here will be 15, and this number here will be 4.8 times 2, and the WF will be twice as much, and the bending moment will be twice as much. And guess what? When we find area of steel, you will get area of steel, which you have to place it in your 2 meters.
And then that's just over designing, right? If we did the Mahdi method.
It will give you the same results. If you use 1 meter wide, you will get 1 bars in 1 meter. And if you use 2 meter wide, you'll get 10 bars in 2 meters, which means in 1 meter it's 5 bars. Is that clear?
Yeah, makes sense.
So it's not over designing. It's not over designing anything. It is just an agreement that my width of my design strip is going to be 1 meter. I will get the load on 1 meter. I will find the bending moment on the 1 meter. I will find the area of steel in that meter. If you chose design strip 2 meter, you will find the load on the 2 meters. So you multiply all the numbers by 2. You will find double the moment that you get for 1 meter. You will get double the area of steel, but you place it in 2 meter, not 1 meter. So you end up with the same thing. Hopefully this is clear. Any question for now?
Ramin, can you please explain the transverse and reinforcement again?
The transverse area, I said, guys, 100% of the load will go into, read this please, Toyib, read this please. So I said 100% of the load will go into the shorter direction based on the moment. The perpendicular direction is called transverse, okay? And it carries no load. No load will go into the transverse direction. But I'm still adding here reinforcement perpendicular to my red reinforcement. It will go into the blue. Why? Because the slab integrity, it's over there, and because of secondary stresses like thermal stresses and shrinkage stresses. Guys, concrete, if you make concrete without any reinforcement, what happens is it tries to shrink, and if there is no reinforcement, it will crack. Any other questions before I say goodbye for you guys?
Taher, so the depth of the slab is always going to be related with the size of the beam.
Say it again, sorry.
The depth of the slab, you always estimate that with the size of the beam.
No, sir. No, sir. The depth of the slab, you can look at the equation. The thickness of the slab is connected to the clear span. So look at this. Clear span is what controls thickness of your slab. The thickness of your beam, for example, let's be clear. So let's do that. So the thickness of your slab is based on this dimension from here to there. The thickness of the slab will be function of 750. That's what controls mils. That's what controls the thickness of your slab. How about the thickness of your beam? It is function of the beam span, which is between the column. So between the column, that's the beam, and this is something, probably it is 7 meter or something, 7,000 mils. Is that clear, guys?
Yeah, thanks.
Beam thickness is function of the beam span. Slab thickness is function of the slab span. Okay, guys. So if you are okay, I'm so tired, so I'll let you guys go. Have a good day. Thanks.
Have a good day.
You too.
Thank you, sir.
Thank you.